computer and share screen. Okay, okay, so Quicksort. Way Quicksort works, and this is how I typically like to write my things, is I just simply put everything in, I just take all the numbers and throw them wherever they need to go. Although with Quicksort, where I'll probably want to stack the deck a little bit so that I can three, four, 5, 6, 1, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So we'll go ahead and do this as my array. So what we do with Quicksort is that when we pass it into the Quicksort function, and then the first thing we do is we pass it into the partition function. So this is either an array or a subarray, and we have basically a left as the index and a right as the index. Okay. When left and right swap places, we're done with Quicksort, essentially. Okay, or we're done with that branch of Quicksort, because that's, you can't, that no longer makes sense. But basically, you have the left side of your array or subarray and the right side. Okay, so what we do is that we have, again, the way Quicksort works is that you select the pivot item and you shove everything to less than to the left and everything greater than to the right. But how do you actually do that shoving if you don't want to use any auxiliary space? If you don't want to use any extra space? Okay. So what we do is that we leave that question of choosing a good pivot for later discussion, and we're just simply going to select the leftmost item of the subarray, the leftmost item, in other words, left, as our pivot. So this item is also, so left is going to act as our pivot. Make sense? Next, we set up two variables. The first one is called up, and the second one is called down, which are also on left and right, respectively. Left and right won't move, but up and down will. Now we search up the arrays in ascending values of indices for the first value that is bigger than our pivot. Okay, so we search up for the first value bigger than our pivot. Make sense? So we know what the pivot is. It's 5, right? So we search up. And then once we find a value that is bigger than our pivot, we stop up there. So makes sense? We found 6 is the first value bigger than our pivot. So we stop there. Then we search down. Okay, for the second value, for the first value that is smaller than our pivot. This is down. Now that we have that, now that we found them, we swap them. 3 and 6. We can, and then we continue. We keep doing this until up and down swap places. So up for the first thing that is bigger. Down for the first thing that is smaller. Then again, our pivot. And now we swap those. 7 and where they were 7 and 2. So now I'm sure. So it's now 2 and 7. All right. Now again, we look up for the first thing that's bigger, down for the first thing that is smaller. Now, because up and down have switched places, we can stop this swapping thing. Because if you check out what we've got here, we've now got it kind of separated. We've got it partitioned into 3 pockets. We've got the left, the right. Sorry, we've got the pivot. We've got everything less than the pivot and everything greater than the pivot. Okay, but now. What we want is everything less than the pivot, and everything greater than the pivot, right? And again, left and right are indices as well as down and up. Those are indices. So what we can do is that we can swap the values. And what we're going to do is that we are going to swap the value at the pivot, the pivot value with the value at down. Okay, so we swap 5 goes over here and 2 goes over here. Okay, so we swap those values. And then the partition function returns this value down. It returns down. That is the index that the pivot is at. Make sense? And so now what you can do is that basically that you will call, once now that that's done, you can call quicksort. You can call quicksort on left to the pivot index -1, and then quicksort on the pivot index +1 to right. Okay, and that will recur, and that will be recursive. Make sense? Now, on average, this runs in O of n squared time. Sorry, not unsquared. It runs on average of n log n, with the caveat that it could run worst case time scenario of O of n squared. Now, when will it run in O of n squared? When this naive method of doing quicksort, which is in place, but it's naive in the sense that it doesn't work any better for selecting the pivot. So the pivot, so the quicksort itself is good. The pivot selection is not so much. If we keep selecting bad pivots over and over again, so like if I select my pivot being 1, then my pivot is 2, then my pivot is 3. I'm only sorting one item at a time each call, as opposed to basically here we're able to reduce the number of calls we do substantially, because we're splitting it in half each time. Now, the way we get around this in the real world is that we select good pivots. We select good pivots. So one way to select good pivots is to like try to approximate what the median value of your subarray is. Because if the closer our pivot is to the median, then the better our runtime will be, the better the partition results are going to be. So one way to do that is like take the first item, the middle item, and the third item, and then kind of sort them to figure out which is the so that you'll have a better odds of getting a good pivot. That's one way suggested in the book. Another way that Java does it is that it uses a refined version of quicksort that uses not 1 but 2 pivots, using a 2 pivot quicksort, so that it can and the way it handles everything, and I haven't looked into it, I just read the documentation, so I know it exists. But what the documents say is that does not reduce that does not basically turn into the O of n squared nearly as often as other quicksort algorithms. But the idea behind quicksort is that you still is that pivot, but doing it in place helps with that selection a whole lot. On the final exam, you'll be expected to know how to do the partition algorithm. Okay. Okay.